Hello guys, welcome to Psychology Corner. Today we are going to study about action potentials. Information moves along a neuron in the form of a neural impulse called an action potential. An electrochemical impulse that travels from the cell body down to the end of the axon. Each action potential is a result of the movements of electrically charged molecules known as ions. In and out of the neuron, the key to understanding the generation of an action potential lies in appreciating that neurons are normally very selective about what ions can flow in and out of the cell. That is, the cell membrane of the neuron, including its axon, is semi-permeable, which means that some ions can pass through the cell membrane easily and others are not allowed to pass through it, except when special passageways in the membranes are open. These passageways, called ion channels, are duff-neck-shaped protein molecules that form pores across the cell membrane. These proteins regulate the flow of ions such as sodium, potassium, and chloride in and out of the neuron. You may be more familiar with the term natrium for Na+ and kalium for K+. Each ion channel is selective, permitting only one type of ion to flow through it and when it is open. The importance of sodium potassium the importance of sodium Na+ ion channel is shown by the effect of local anesthetic agents such as Novocaine, which is routinely used to numb the mouth during dental procedures. Novocaine prevents sodium channels from opening, thus preventing sensory signals from reaching the brain. When a neuron is not generating an action potential, it is referred to as resting. At rest, the cell membrane is not permeable to sodium ions, and these ions are found at a high concentration outside the neuron. In contrast, the membrane is permeable to potassium ions, which tends to concentrate inside the neuron. Certain protein structure called ion pumps help to maintain this uneven distribution of ion across the cell membrane by pumping them into and out of the cell. For example, the ion pumps transport sodium out of the neuron whenever it leaks into the neuron and transport potassium back into the neuron whenever it gets out. In this way, the resting neuron maintains a high concentration of sodium outside of the cell and low concentration inside it. This overall effect of these ions channels and pumps is to electrically polarize the cell membrane of the resting neuron, keeping the inside of the neuron more negative than the outside. These electrical potential of a neuron at rest is termed as resting potential. For most neurons, the resting potential is around minus 70 millivolts. The resting potential of a neuron is similar to the charge held by a battery. Both neurons and batteries use electrochemical breakdowns to store energy. The neuron's energy can be used to generate action potentials. How does this happen? The electric potential across a neuron cell membrane will change if it is stimulated by other neurons. This stimulation is caused by the action of neurotransmitters that are released by the presynaptic neuron and received by the postsynaptic neuron. If the change in electric potential is very small, nothing dramatic will happen. For example, if the potential is raised to about minus 60 millivolt or so, the neuron's ion pump will quickly restore the resting potential of minus 70 millivolt. However, if the change in electric potential is large enough, a different set of events occur. For most neurons, minus 55 millivolt constitutes the excitation threshold. If the electric potential is raised above this value, the cell membrane becomes temporarily unstable, resulting in an action potential. In other words, the initial depolarization caused by external stimulation raises the potential above threshold. This leads to a cascade of events that result in a temporary reversal called depolarization of the potential across the membrane. First, voltage sensing sodium channels located on the axon suddenly open so that sodium ion can now cross the membrane into the cell. These positively charged sodium ions will flood into the cell because opposite charges attract one another and the inside of the cell is negatively charged. Now the inside of that area of the axon becomes positively relative to the outside, going up to about plus 40 millivolt or so. Next, some other positively charged ions, in particular potassium, are forced out and the ion pumps begin to restore the electrical balance across the cell's membrane to its original state. This entire process takes only about milliseconds and the resulting spike in electric potential is called action potential. The action potential will propagate itself down the axon in the direction of the terminal buttons. This is because neighboring sodium ion channels sense a voltage drop and often causing the adjacent area of the axon to depolarize. This process repeats itself down the length of the axon. The reason that an action potential travels only in one direction and not in backwards is a result of refractory fever. After it has generated a spike in a membrane, cannot do so again for about 1 millisecond. The speed of the action potential as it travels down the axon can vary from about 1 to 120 meters per second. The speed is affected by whether the axon is covered with a myelin sheath. This sheath consists of specialized glial cells that wrap themselves around the axon, one after another with a small gaps between them. These tiny gaps are called the knots of Ranvier, named after the French anatomist. The insulation provided by a myelin sheath allows for saltatory conduction, in which the nerve impulse jumps from one node of the Ranvier to the next. This greatly increases the speed of transmission of the action potential down the axon. Saltatory comes from Latin and saltere, which means to be. The myelin sheath is particularly prevalent and rapid transmission of the action potential is critical. For example, along axons that stimulate the skeletal muscles. In multiple sclerosis, a disorder in which symptoms first becomes evident between the ages of 16 and 30, the immune system attacks and destroys the body's own myelin sheaths, producing severe motor nerve dysfunction. This is for today. I will come up with another video. Thanks for watching. Take care. Goodbye.